Hi, class. Good morning. Today I'm going to talk about another type of inheritance. Last week talked to you about simple Mendelian monohybrid crosses, where we were looking at the inheritance of one trait that was a trait that is controlled by a gene that has two different alleles, one being the dominant, whereas the other one being the recessive allele. And we went through a number of genetic problems to go through different parental crosses of and to show the probability of having different types of offsprings in terms of genotypes and phenotypes. There are two other types of inheritance that I wanted to discuss with you, but I feel that as we're going through this COVID-19, everything needs to be compressed a little bit, and I didn't see the need to include those other two, and it might be a little confusing going through all four types of inheritance with you. So the final type of inheritance that I wanted to discuss with you and teach you was known as sex-linked inheritance. And this is a type of inheritance in which the traits are controlled by genes located on the sex chromosomes. And that's why they are called, this type of inheritance is called sex-linked. So traits controlled by genes on the X chromosome are called X-linked traits because males only have one X. They are affected by what are known as recessive X-linked traits more often than females are, because females have the other X chromosome, which might have a allele that is dominant and normal, which will mask the recessive allele that is basically the abnormal condition, or would represent the abnormal condition. So we're going to go through this in this slideshow right now. So we're talking about these right here. These are the sex chromosomes. These are all the other types of chromosomes. They're also known as autosomes. We've talked about this before. And this is, I'm going to go over this type of diagram with you in another lesson, but this is called a human karyotype. So what are sex-linked traits? And let me just increase this to show that. Okay. So traits, again, controlled by genes located on the sex chromosomes. These are the X and Y chromosomes. Most of these traits are X-linked. The Y chromosome is really, really tiny. If you can, let me go back to show you. You see this Y chromosome is a lot shorter than the X chromosome, and therefore it's going to have a lot fewer genes. And that's why most of those sex-linked traits are X chromosome linked or X-linked. The symbol for the allele is attached to an X or Y in sex-linked inheritance patterns. So, for example, this is considered the genotype of a male individual, and the X chromosome will have a dominant allele, capital H, and the Y doesn't have. The Y chromosome does not have any alleles, so there will be no symbol attached to the Y. In the case of the female, both of the chromosomes are X chromosomes, and in this case we have a heterozygous genotype where you've got one X chromosome that carries the dominant H allele, and the other X chromosome carries the recessive allele, which is represented by a lowercase letter. And when you do this cross, you see that you will have basically the probability is having 2 females and 2 males. And this particular male will, if H, whatever condition or trait that H is, let's say, having hemophilia, for example, or being normal. Let's say H represents normal, and this male would be normal. If little h represents the abnormal condition, which is a hemophilia, then this male would have hemophilia. This female would be completely normal because she has big H, big H. This female would have a phenotype of being normal, but she's what is known as a carrier because she does carry that recessive H allele that could basically codes for hemophilia, and she can pass on that hemophilia allele to her offspring. So this is what this looks like over here, another karyotype. So males are more affected by recessive X-linked traits. This is because males only have one X chromosome. Again, there's no other allele to dominate over the recessive allele. So if you have, in this case, X big, this is a female genotype, 2 X's. If you have the dominant allele to represent a normal condition, then the normal condition is expressed. It masks the recessive allele. In the case of that male, this is a male genotype, X and Y. The D is expressed because there's nothing to mask that D. It's a dominant allele. And there's nothing to mask it or counter it on the Y allele. If the female has little d, then the D is expressed. Obviously, there's nothing to mask that little d, and that this female will have that condition or trait that is recessive. And then in this case, this is the male, and he will have that condition or trait as well because there's nothing on the Y that's going to mask that little d. Okay, and this just shows you again the size difference between the X and the Y alleles. So these are genes right here that these particular alleles do exist on the Y chromosome, but for A, B, C, there's nothing here on the Y chromosome that can basically mask these alleles. So if the male has these on his X chromosome and there's nothing to mask it on the Y chromosome, then he will express these alleles. So there's a number of different examples of sex-linked inheritance, and one such example is called red-green color vision deficiency. Okay, so this particular deficiency can affect about 8 to 10% of males, and only about 0.5% of women are affected by this form of color vision deficiency. Hemophilia is another condition that is another example of an X-linked recessive condition. It is where the individual, if they have the hemophilia, they are more susceptible to bleeding out because their blood has a inability to clot normally. So if they cut themselves, like, it could be quite lethal. They have to be very, very careful because of the fact that their blood doesn't clot and it just keeps bleeding. Duchenne muscular dystrophy is also an X-linked recessive condition. This condition causes muscle degeneration. And then Fragile X syndrome. This is X-linked dominant condition. So if you have this allele, the dominant allele makes the person express this condition. So can cause mental and social disorders. And Rett syndrome is, hold on a second, I'm trying to make this a little bit longer. It's also an X-linked dominant condition, and you can have neurological disorders as well. Oops. So now there's a whole bunch of different types of problems, genetic problems associated with sex-linked traits. So I'm going to do a few with you right now, just to give you an example, a few problems, example problems. So red-green colored vision deficiency is an X-linked recessive disorder. A male with normal vision marries a heterozygous female. What is the chance the couple's first child will be a male with normal vision? So first of all, we have to have the alleles. We need a legend, and we need to choose the letters for the alleles that we're going to have. So I'm going to use capital N for normal vision, because that is a dominant. This is a sex-linked recessive disorder. So big N would be normal, and little n, and I'm writing up right now. I'm not writing like I normally would do on a piece of paper. That's why it's very, very messy. I'm so sorry. But anyways, this is basically the little n will represent red, green color vision deficiency. Okay, so we're going to have to find out what the parents are. What are the parents' genotypes? So a male with normal vision. So a male, this is basically represents a male. This is the symbol for a male. This is the symbol for a female. So the male parent is going to have this genotype. Okay. The male is an X and Y, represented by an X and Y chromosome, and they say that he has normal vision. That means you have to have the X chromosome with the capital N, because that's what normal vision represents. And he marries a female that is heterozygous for that allele. So that means she's got one big N on one X chromosome, and she's got one little n on the other chromosome. So let's do the Punnett square to find out what the probability of the children will, like what genotypes and phenotypes will most likely be created by this cross of these two particular types of parents. So the first child is going to be X big N, X big N, which is a normal one. And then the next child is going to be a boy. This is a girl. This is a boy, big N and Y. And then we're going to have X little n, Y, and X little n. Oh, sorry. This one should be X little n, Y. Oops. And then this one is X little n, Y. Make sure I've done this correctly. And I haven't. So big N, big X. So we have this, okay? So the question is, what is the chance the couple's first child will be a male with normal vision? So this is your male with normal vision, and that is basically, it's a 25% chance. the couple's first child will be male with normal vision. And the reason why it's 25% is because, first of all, you've got four different offspring there. This is another male, this one right here, but this male has red-green color vision deficiency because he's got the little n. So, and then these two are females. So one out of those four was the male that has that is a normal male. So that's why it's 1 out of 4 is also 25%. Okay, so that's that question. Number 2, Fragile X syndrome is a dominant X-linked disorder. If a hetero female has a child with an affected male, what is the chance of the child having Fragile X syndrome? So now we are going to do our legend again. Capital F is basically Fragile X syndrome. And again, I'm really sorry for my messy writing here. And then little f would represent normal, okay, a normal individual. And then we've got we want to draw our parents. So the heterozygous female heterozygous has a child with an affected male. So female is, let's just do the male first. So if male is got the big F, he's affected, times the heterozygous female. So she's got big F and small f. Okay. So let's do the F1 generation. This is where we have to do the cross. So we'll put the male on that side. We'll put the female on this side. So the first one is a female that has both big F's. Then we have a male here that is normal. And then now we have a female that is heterozygous. And then lastly, we have a male that has a Fragile X syndrome. So we've got this male here. What is the chance of having a male with the Fragile X syndrome? Again, 1 out of 4 means 25% chance. The child will have Fragile X syndrome. Okay, next one, last one. Hemophilia is a recessive X-linked disorder. A normal woman whose father had hemophilia marries a normal man. What is the chance of the couple having a hemophiliac child? Okay, so first of all, let's just do our legend. This is basically normal. Okay, and normal individual, big H, because it's hemophilia is recessive X-linked. So little h is going to represent hemophilia. Okay, and we're going to draw or write down what the parents are. Now, the father, a normal woman whose father had hemophilia marries a normal man. So let's just write down what the man is, because we know normal means big H. Okay, and the female, we know she's going to be big little XX, but the father had hemophilia. So we know, even by not us being told that she's heterozygous, she's heterozygous. She's normal. That means she has to have the big H, but her father had hemophilia, but so he must have passed on that hemophiliac allele to her. So now we're going to do the cross. So we're going to do X, the male on one side and the female on the other side. So we're going to have one normal, this is a homozygous dominant female, and then we're going to have one normal male. We're going to have one heterozygous female who she's a carrier, and then we have this affected male as well here. So what is the chance of the couple having a hemophiliac child? So again, these 1, 2, 3 are going to be normal. The only one here that has hemophilia is this male child. So there's 25% chance of couple having a hemophiliac child. Okay? And so those are the three problems that are associated with sex-linked traits. Another one that we haven't really discussed, and it's quite, a lot of students get a kick out of this, is that a male pattern baldness is also a sex-linked inheritance trait, basically. So the allele for baldness is recessive in females but dominant in males. So causing hair loss that follows a typical pattern is called male pattern baldness. And so if a male is bald if he's heterozygous for the trait, while a female is bald only if she's homozygous recessive, because of the fact that in females it's recessive, the allele is recessive, and in males it's dominant. So it's kind of a different pattern of inheritance, male pattern baldness. So the key thing for you guys to know for this sex-linked traits is the fact that the most important thing is that what are the genotypes of a male compared to a female, and the whole idea of the fact that on the Y chromosome there's very, very few alleles that can mask that X chromosome allele in a male. So that's why it's kind of important that we learn about sex-linked traits. Anyways, I hope you understood the lesson. I'm going to give you a bit of reading and some practice problems in the lesson as well in the post. Take care and have a wonderful day.